Transition metals have three superpowers that show up everywhere. They make intensely colored compounds. They speed up reactions as catalysts, and they can switch oxidation states like changing gears. The engine behind all three is the same idea: coordination chemistry. The D block is the middle of the periodic table, the transition metals. What makes them special isn't that they're complicated. It's that they have electrons in a set of orbitals called d orbitals that can be rearranged, shared, and promoted in ways that make their chemistry unusually flexible. Now the key move: transition metals don't just form simple salts. They form complexes. A complex is a metal ion surrounded by ligands molecules or ions that donate electron density to the metal. Think of the metal as a hub and the ligands as connectors. Change the ligands, and you often change the color, reactivity, and stability. These ligands don't arrange randomly. They adopt shapes, often 6 around the metal. Sometimes 4, and the shape matters because it changes how the d electrons feel their environment. Here's the color mechanism. In many complexes, the ligands split the d orbitals into 2 energy levels. White light contains many colors. If the complex absorbs one specific color because that photon matches the energy gap, then the color you see is what's left over. That's why small changes around the metal can shift the color dramatically. Different ligands, different splitting, different light absorbed. This is also why you'll see the same metal ion look different in different solutions. The metal didn't change, the ligands did. Coordination chemistry is color chemistry. Next superpower: variable oxidation states. In many transition metals, the outer s and d electrons are close in energy, so removing or sharing one more electron doesn't completely wreck the atom's stability. That gives you multiple accessible oxidation states. And that matters because oxidation state is basically the metal's electron bookkeeping, how many electrons it can accept, donate, or share in reactions. Now catalysis. A catalyst speeds up a reaction by offering an easier pathway, like replacing one tall hill with 2 smaller hills. Transition metals are brilliant at this because they can temporarily bind reactants, shuffle electrons between oxidation states, and then return to their starting state. They do chemistry without being consumed, like a skilled negotiator moving electrons between partners. Sometimes the catalyst is a metal surface molecule stick, weaken bonds, react, and leave. Sometimes it's a dissolved metal complex that binds a molecule, changes it, and releases it. Different look, same core advantage. Transition metals are good at temporary relationships. This is why transition metals sit at the center of modern chemistry. Catalytic converters cleaning exhaust, industrial catalysts making essential chemicals, metal complexes driving selective reactions, and the characteristic colors that let you track what's happening in solution. If you want one practical lens for D-block chemistry, it's this control panel. Which metal is it? What oxidation state is it in? And what ligands and shapes surround it? Those 3 knobs explain most of the color, most of the reactivity, and a lot of the catalytic behavior. Now that you've seen the engine, which transition metal superpower feels most surprising? Color from light absorption, switching oxidation states, or catalysis? Subscribe for more interesting videos from Truth Through Texts.